The universe shouldn't exist. Not like this. Not with stars, planets, or you watching this video. That's because the laws of physics say the Big Bang should have made equal amounts of matter and antimatter, and when they meet, they annihilate into pure energy. In a perfectly balanced universe, there'd be nothing left. Just a smooth sea of radiation. Forever. But maybe the antimatter isn't missing. Maybe it's somewhere else. In a hidden mirror universe, running backwards in time. Matter and antimatter are identical twins in almost every way. Same mass, same spin, same behavior under the forces of nature. The only obvious difference is their charge. An electron is negatively charged. Its antimatter twin, the positron, has the same mass, but a positive charge. A proton is positive. Its antimatter twin, the antiproton, is negative. Put them together, and they annihilate in a flash of pure energy, gone as if they never existed. And here's the thing. Our best understanding of the Big Bang says it should have created matter and antimatter in equal amounts, perfectly balanced, every matter particle paired with an antimatter twin. But that's a problem, because in a perfectly balanced universe, all those pairs would have found each other and wiped each other out. No galaxies, no stars, no planets, no you. Just an empty, featureless cosmos flooded with high-energy light. Yet here we are, in a universe overwhelmingly made of matter. Antimatter exists, we can make it in particle accelerators, and it shows up fleetingly in cosmic rays, but it's vanishingly rare compared to matter. If vast regions of antimatter were out there, galaxies, clusters, even stars made entirely of it, we'd see the borders where matter and antimatter meet. They'd blaze with gamma rays from annihilation, but the sky is quiet. There's no sign of such boundaries anywhere we look. This is one of the deepest mysteries in cosmology. It even has a name, the baryon asymmetry problem. Somehow in the early universe, matter won, not by much, maybe one extra particle of matter for every billion pairs that annihilated, but enough to tip the cosmic balance. So the question is, why? Why do we live in a universe that's almost entirely matter when the laws of physics say it should have been a perfect tie? And here's where one of the boldest ideas in modern cosmology steps in, an idea that doesn't just explain the missing antimatter, it gives it a home. So, where did the antimatter go? What if I told you it never disappeared at all? What if it was never destroyed, never scattered, never lost, but instead it's been living its own existence in a universe that is the perfect mirror of our own? This is the heart of something called the CPT symmetric universe, one of the boldest and most elegant ideas in modern cosmology. CPT stands for charge, parity, and time. Three symmetries that, taken together, form one of the most unshakable principles in physics. Charge, flip matter into antimatter. Parity, flip the universe as if in a mirror, swapping left and right. Time, run everything backwards, so causes become effects, and effects become causes. Here's the astonishing part. The laws of physics don't break when you do all three at once. They carry on as if nothing happened. Normally, we think of CPT symmetry applying inside our universe to the behavior of particles in experiments. But what if we apply it to the universe itself? The result is mind-bending. The Big Bang isn't the absolute beginning, but a kind of cosmic mirror point. On one side, our universe made of matter, expanding, cooling, and flowing forward in time. On the other, an anti-universe made of antimatter, expanding, cooling, and flowing forward in its time, which to us looks backwards. In that picture, the antimatter from our Big Bang isn't missing at all. It's right there, on the other side of time, forever unreachable, forever balanced with us across the boundary of the Big Bang. Two universes, two arrows of time, and together, perfect symmetry. We're used to thinking of the Big Bang as a single event, an explosion in which everything began, time itself bursting into existence and running in one direction, forward. But in the CPT symmetric picture, the Big Bang is something else entirely. It's not the start of a one-way journey, it's a Janus point, like the exact centre of an hourglass, where two opposing flows meet and then diverge. From that moment, two universes expand in opposite temporal directions. One is ours, matter filled with time flowing forward as we know it. The other is the anti-universe, antimatter filled with time flowing forward for them, but backwards from our point of view. Each side experiences its own arrow of time, defined by the growth of entropy, the natural increase of disorder. To them their future looks as clear and inevitable as ours does to us. This symmetry has surprising consequences. Because both universes start out perfectly smooth and uniform, it naturally explains some of cosmology's biggest puzzles. Take the horizon problem. In our standard model, distant regions of space look almost identical in temperature and structure, even though light and heat should never have had time to pass between them. Inflation was invented to fix that by stretching the universe in a fraction of a second, but in the CPT symmetric view, there's no need for such a stretch. The smoothness isn't something the universe had to earn through inflation, it's built into the symmetry of the two halves. The same goes for the flatness problem, the strange observation that space is balanced on a knife edge between eternal expansion and rapid collapse. The CPT model makes that flatness a natural outcome, not a cosmic coincidence. And all the while, it's quietly solving the mystery of the missing antimatter, not by destroying it, but by giving it an entire universe of its own. The beauty of the CPT symmetric universe is that it doesn't just sound elegant, it makes predictions, real testable predictions that could prove it right, or kill it completely. Prediction 1. Dark matter isn't a mystery particle from some endless menu of possibilities. In this model, it should be a very specific thing, a stable right-handed or sterile neutrino with a mass of around 4.8 times 10 to the 8 giga-electron volts. That's more than 100 million times heavier than a proton. If that sounds exotic, it is. Sterile neutrinos don't interact through the electromagnetic or strong nuclear forces, only gravity and maybe the weak force. They'd be invisible to us except through their pull on galaxies and clusters. And this particular mass isn't arbitrary. It drops straight out of the equations when you enforce CPT symmetry. Prediction 2. Neutrinos should be Majorana particles, meaning each one is its own antiparticle. That's not just a trivia fact. It means a rare process called neutrinoless double beta decay should be possible, where two neutrons decay at once and no neutrinos come out at all. If we detect that, it's a major point in this theory's favour. Prediction 3. The lightest of the three known neutrino types should have zero mass. Not close to zero, not too small to measure, but exactly zero. If experiments ever pin down a non-zero mass for that lightest neutrino, CPT symmetry in this form takes a serious hit. And prediction 4, there should be no primordial gravitational waves from the Big Bang. In cosmology, these show up as B-mode patterns in the polarization of the cosmic microwave background, subtle swirls that inflation predicts should exist. But the CPT model doesn't need inflation, and it says those B-modes simply won't be there. 4 predictions, 4 ways to check, each one an opportunity for this idea to rise or to fall. And right now, the experiments are already underway. A theory this bold can't just sound good on paper. It has to stick its neck out. It has to make claims so clear that one solid measurement can prove it right, or wipe it off the map. And that's exactly what makes the CPT's symmetric universe so fascinating. It's not hiding in the shadows. It lays down 4 tests, each one a chance to confirm it or crush it. So how do you test a theory this wild? How do you find out if a mirror universe really exists? You go after it, one test at a time. Test 1. The heavy, sterile neutrino. The CPT model singles out a very specific mass for dark matter, far beyond the reach of any accelerator. That forces astronomers to look for indirect clues, tiny imprints in the arrangement of galaxies, or subtle patterns in the light from the early universe. A confirmed signal at that exact mass would be hard to explain any other way. Test 2. Neutrinos as Majorana particles. If neutrinos are their own antiparticles, some nuclear decays should happen without emitting any neutrinos at all. Detectors buried deep underground like Legend in Germany and Nexo in Canada are watching for this ultra-rare event. Even a single clear detection would be a major win for CPT symmetry. Test 3. The lightest neutrino has 0 mass. We can now weigh neutrinos with extraordinary precision. In the lab, Katrin in Germany measures the energy of electrons from tritium decay. Across the cosmos, galaxy surveys search for faint blurring caused by neutrinos drifting through space. If both agree that one neutrino is truly massless, the CPT model survives another round. Test 4. No primordial gravitational waves. If the CPT picture is correct, the universe didn't inflate, and the telltale B-mode swirls in the cosmic microwave background should never appear. Observatories like Simon's in the upcoming CMB S4 are hunting for those twists right now. A detection would be a heavy blow. Continued silence would strengthen the mirror universe case. That's the risk and the beauty of a theory that's this specific. A single clear result could crown it or crush it, and those results are already on the way. And if even one of these tests tips in its favour, then our picture of reality will have to change. Time, matter, the very structure of the cosmos, all reframed through the lens of a universe that is only half the story. Which brings us back to what this would really mean for us. And if even one of these tests tips in its favour, then our picture of reality will have to change. Not in some minor academic way, but in a way that rewrites our place in the cosmos. Because it would mean time itself is not universal. It isn't a single arrow fired at the Big Bang, carrying every star and every moment forward in lockstep. Instead, time's arrow is local. It's simply the direction in which entropy, disorder, grows for you. In our universe, that direction points away from the Big Bang. In the anti-universe, it points the other way. But here's the twist. To them, nothing feels reversed. Their forward feels exactly like ours does to us. From their perspective, we are the backwards ones. Our galaxies spiraling the wrong way. Our stars collapsing into dust before they ever shine. Our cause and effect flipped. And yet, in the strange symmetry of physics, both sides would be right. Both sides would be normal in their own frame of reference. The Big Bang, then, wouldn't be the dawn of everything. It would be the hinge between 2 great doors, each swinging open into its own reality, each containing its own history, its own future, its own version of forever. You could imagine them like 2 rivers springing from the same hidden spring, flowing in opposite directions, never meeting again, yet forever linked at their source. Or like the facing pages of a book, each telling a different story, yet bound in the same volume. And somewhere, far beyond any horizon we can ever reach, there could be civilizations living in that mirror cosmos, born of antimatter, writing their own myths, never knowing we exist, just as we have never known about them. If this picture is true, then we are not the whole story. We are not even the whole universe. We are one half of a cosmic symmetry, two arrows of time launched from the same instant, vanishing into opposite eternities. We are like twins separated at birth, alike in countless ways, yet through cosmic misfortune, destined never to meet again. And maybe, just maybe, we can only sense each other through the faintest of indirect clues. It's a reminder that the cosmos is under no obligation to make sense to us, and that reality may be deeper, stranger, and more beautiful than we can yet imagine. Like any bold idea, the CPT symmetric universe has its hurdles. The first is practical. That heavy sterile neutrino it predicts, we may never be able to detect it directly. It's far too massive for any particle accelerator we can imagine building, and it interacts so weakly that it would slip through detectors like a shadow through sunlight. The second is observational. The anti-universe itself is unobservable. By definition, it lies beyond the Big Bang horizon. We can't point a telescope at it. We can only look for the indirect clues it leaves behind in the structure of our own universe. This is a sticking point for many physicists. If something can never be seen, how do we know it's really there, and not just a beautiful story? There are also alternative explanations for the missing antimatter. Some theories suggest tiny violations of symmetry in the early universe, processes that would let matter slowly win over antimatter without invoking an entire mirror reality. Even its strengths can be weaknesses. The absence of primordial gravitational waves, for example, would support the CPT picture, but it could also happen in other models. No single test is a perfect smoking gun, and so the CPT symmetric universe sits in a delicate position, bold enough to be exciting, constrained enough to be falsifiable, but still waiting for that decisive piece of evidence. Until then, it remains one of the most intriguing and most debated ideas in cosmology. If you enjoy exploring the strangest, most beautiful ideas in science, subscribe to Stellar Stories for more deep dives into the mysteries of the cosmos. Because sometimes the universe has more to tell us than we ever imagined.